is that a projectile is being launched along the ground that is not flat. So in this problem, we've got a projectile that's being launched from the base of a hill that rises at some angle. Let's say that angle is 30 degrees, I'll call that phi, and the projectile itself is going to be launched at an angle with respect to horizontal, which we'll call theta. Let's say that's 45 degrees. And let's say the launch speed of this projectile is 50 meters per second. I want to know when this thing lands on the hill, how far has it traveled along the hill before it lands? Okay, so the first thing I would do with a problem like this is establish a coordinate system where the projectile starts from the origin, and I'm going to keep the x and y axes oriented horizontally and vertically. A lot of times when you solve problems with objects that are sliding along a hill, you will rotate the axes to align them such that one axis is parallel to the surface and the other is perpendicular. The reason you do that is because you usually want the axes to be oriented such that the acceleration is only in one direction. So in this problem, the acceleration is going to still be vertical, so I want my y-axis oriented vertically. So when I do that, I can write the usual equations of motion that will give me the x and y position of the projectile as a function of time. So in the x direction, we will just have v times the cosine of theta multiplied by t. And in the y direction, we will have the position being v times the sine of theta multiplied by t minus 1/2 g times t squared. Okay, so what we need to do is figure out an expression for the time when this projectile lands on the ground. And usually the way you do that is you set the final position in the y direction to be 0. Here, that's not the case. When this thing lands, it's going to have some positive y position due to the way that we've defined our coordinate system. So instead, what we have to do is we have to find a way of expressing the set of all of the points along this line. So essentially, we just need the equation for the line that describes the slope. Well, this is just a straight line through the origin, so that should be a linear function. So the question is, how do we express the slope of this line in terms of the angle phi? So the slope of this line would be measured by just taking the ratio of some change in the y direction divided by the corresponding change in the x direction, but notice that's just the same as the tangent of the angle. So the equation for this line would simply be y is equal to the tangent phi times x. So now what I want to do is just take these two equations here, substitute them into the equation for this line, and solve for the value of t. So when I do that, I will get v sine theta t minus 1/2 gt squared is equal to v cosine theta tangent phi times t. All right, so I need to solve this equation for t. I can cancel one factor of t from every term and then move some things around. That will give me 1/2 gt is equal to v times the sine of theta minus cosine of theta tangent phi. And then a couple more steps give me that the time is equal to v times sine of theta minus cosine theta tangent phi, all multiplied by 2 and divided by g. So when I plug in all of the numbers that I gave at the beginning of the problem, I won't go through the details there. We should get that the projectile lands at a time of about 3.05 seconds. Okay, so now we know the time when this thing lands, so we can just plug that into these two equations here and find the x and y position of the object, and then we can use the Pythagorean theorem to solve for the distance along the incline. And when we do that, let me give this a different name here. I'll call this t sub land. So the distance along the incline is going to be the square root of x evaluated at this time squared plus y evaluated at this time squared. And again, when I put in those numbers, I'm going to get a distance right around 124.5 meters.